everyone. My name is Dr. Valerie Meyer-Spiridolozzi, and I teach Industrial and Systems Engineering here at the University of Rhode Island. The Yukon URI Navy STEM Coalition works with the National Institute for Undersea Vehicle Technology and our partners throughout the region who build submarines and support the U.S. defense industries. Come take a look what we're doing.
Hello, young scientists and engineers. My name is Dr. Gretchen Macht, and I'm an associate professor here at the University of Rhode Island in Industrial and Systems Engineering. As Industrial and Systems Engineers, we work with systems of various areas. What systems have you been investigating in your classroom? It sounds like we are working on very similar things. As engineers, we work with queuing theory, simulations, and operations research, and apply this knowledge to the election system. Come check out what we're working on at the Engineering for Democracy Institute. You may be wondering, why engineers are working in elections? Well, the voting process, so the act of voting, is actually all a system. What do you know about voting? In the United States, voting is a right for all citizens. Voting is a way for people to make decisions and choose their leaders within their democracy. When you vote, you have a say in important matters that affect your community and your country. Voting ensures that everyone's voice can be heard. By voting, you help shape the future and ensure your needs and ideas are considered. The Engineering for Democracy Institute, or EDI, utilizes engineering techniques to make data-based recommendations to help election administrators and local election officials overcome current and future obstacles in election science. Industrial and systems engineers use different models to simulate the systems so that we can study it, understand it, and improve it. So a system is a group of objects joined together in a regular interaction or connection to accomplish a purpose and or function. To simulate a model, it can be described in terms of the input, process, and output, known as the IPO model. So what we're looking at here is the IPO model can also be compared to a bathtub. So in this case, your input or your inflow into the bathtub is water. And that water and that input contains a certain rate or flow, or how fast it then fills up the tub, and then that process fills up as the inflow comes in. Finally, the output is the rate of the water leaving the bathtub. If the water is going faster going into the tub than it is going out of the tub, what do you think will happen? If you guessed that the water would fill up in the tub and then continue, and then maybe if this output isn't going fast enough, if the rate is not high enough as this is, then it might overflow. It might spill onto the floor. So these are challenges that we can look at in engineering by understanding what happens when we have certain processes, how they function, and their inputs and their outputs, and how we can balance that as an entire system. So this is an example of what it could look like in your area when voting in person. What components or elements of the voting system can you think of? So the voting process in Rhode Island specifically, we can look at it in a few different ways. If we remember the IPO model, so the input, the process, and the output model, we can look at as the arrival of voters is the input. We have the process of check-in, ballot marking stations, ballot scanner is your process. And then we can have the departure or the exit of the voter be your output. Or we can have it where there's a lot of those sub-processes. So we have the input of or arrivals of voters, and then that starts the next process of check-in. Then when we have those voters then leave check-in, that is an output or a departure. But then that immediate departure becomes then an arrival or an input for ballot marking stations, right, where you go and you check your ballot, right? Now, when you check that ballot, that is an actual process. But how many questions, how long that ballot is, and how long it takes you to make those decisions is that part of that process. But when you're done and you've got your ballot, you have all the bubbles filled out, you're really excited, then you leave that booth. That is an output. That is a departure from that system, but that departure immediately then puts you back into the input, right? The input of now I have to take my ballot from this sub-process over here, and I now have to do the new process of taking my ballot and putting it into the scanner. And that scanner and putting that into only takes a few seconds. But that's still a process. But when you leave here and you depart this particular station of the ballot scanner, then you depart the whole system for real. So then that's also an output. So when we look at the IPO process, it is a simplification of trying to understand bigger parts of systems. So we can run models that look at it from the arrival, all of this in one process, and then a departure, or we have to do it for each section so that we understand all of the variability, all of the differences, which is better because we get more details, more nuances, those nitty-gritties that we love to make sure that the answer that we give has meaning and value, purpose. Where and how you vote may be very different from how other people vote. And it might be even different from your neighbors next door who might be in a different county and or a different state. One of our jobs at the Institute is to help local election officials and administrators make their voting systems better, and to work with them to create those solutions. This involves us modeling and simulating some real-life polling locations. These simulations are created based on real-time data collected by the EDI or Institute team at real polling locations on election days through a data collection process known as time studies. By analyzing and modeling the processes of a voting system, we can help decrease the amount of wait times for people in order to cast their vote. Let's check out some of the work that we're doing. Here's one of our graduate students now working on this. Hey, Leonie, how are you?
Hi, Dr. Macht.
All right, can you tell us a little bit about yourself and what you're working on?
Hi, everyone. My name is Leonie. I'm a PhD student in Industrial and Systems Engineering, and I do my research with the Engineering for Democracy Institute. Here's an example of a polling location. Our job is to find the optimal layout of the location. Where have you waited in queues or lines before? Have you ever been frustrated while waiting in lines? Why do you think lines form? When we visit the polling location, we make observations about flow and collect data on how long each of the processes takes. Once we have visited the polling location and collected data, we can build a simulation using a software system called Simio to see how we can improve the system to reduce how long people will have to wait in line. Our goal is to use simulation to figure out how the facility should be laid out and how many pieces of the equipment need to be at the location based on the number of people who are registered to vote at that polling location. These calculations are used to help reduce the wait time for people to vote, because if the number of people who enter the system exceeds the system carrying capacity, then people will be waiting in a queue for a long time. We run simulations with different amount of resources to figure out how many resources we need in the end. So when we look at the simulations, we have people walking in, checking in at the station, and then when they are checked in, after a certain amount of time, they're going into the voting booth and filling out their ballot. So as soon one person, they may take longer, and then like at some point when everyone check-in station is full, they're just building a line up. So that's how simulations are running. And when we take off one table, eliminate one, we have probably more people waiting in line. What happens when we have less booths in the end? What happens when we say, okay, we have an unlimited amount of booths? What are the financial costs behind this? We need to buy all this stuff. So therefore, we're using simulations to figure out how many resources are really necessary to meet the constraints. Are there any spaces, rooms, or buildings that you could redesign in your own life? What are some of the problems you see within this space? How could you improve the space to solve some of these problems?
All right, thank you so much, Leonie, for sharing. That was awesome. All right, so this is just an example of the work industrial and systems engineers can do. If you are interested in this work, you should consider becoming an industrial and systems engineer. Maybe I'll see you on campus soon.